All right, in section 4.5, we're looking at optimization again, but in this particular section, we have to actually come up with our own equations. And the first thing that we're going to do is we're going to read through the problem and we're going to assign a letter to each variable that's mentioned in the problem. So any unknowns, we're going to give a variable to. Drawing a picture is going to be really helpful in this section. We're going to find an expression for the quantity that we want to optimize. So we want to maximize or minimize, in other words. And we're going to use the conditions in the problem to write the equation that we want to maximize in terms of only one variable. So that's going to be a significant part of the problem. Then we're going to optimize the function over its domain. All right, so let's look at the problem here. It says the owner of a ranch has 3,000 yards of fencing with which to enclose a rectangular piece of grazing land along a straight portion of a river. So what we're going to do is we're going to have this river, and we want to enclose a little fencing. We want to have a little fence section and the rectangular, but we don't have to have a fence along the river. So the fencing is not required along the river. What are the dimensions of the largest area that he can enclose? So we want to figure out what is the largest area that I can enclose if I only have 3,000 yards of fencing. Okay, we'll call the area A. Now we want to keep in mind that what we want to do is we want to maximize A. So we maximize our area. We have a couple of unknowns here. We don't know how wide that the fencing is going to be. And since those are the same thing, let's call those X. And we don't know how long it's going to be. And since this is going to be potentially a different length, we're going to call that Y. So the area is X times Y, or width times length. All right, so I'm just gonna label this, the width is X, the length is Y. All right, so we know that area is length times width. We multiply those together, we're gonna get the area. Now we want to keep in mind that this is what we want to maximize. Now, the problem here is that we do have an expression for the quantity we want to maximize, but the problem is that it's in two variables. So the key here is that we want to get this in terms of only one variable. So how can we switch everything to be in terms of either X or Y? Well, the secret here lies within the information we're given about the amount of fencing. So what we know is we only have 3,000 yards of fencing available. So that must mean X plus X, we have two of those, plus Y. So that perimeter, when I add all those sides up together, it has to be equal to 3,000. So this is helpful because what we can do is we can rearrange this equation that deals with the perimeter. We can rearrange this to be Y by itself on one side. So let's do that. Y equals 3,000. What we're going to do is we're going to move these two x's to the other side of the equation, so that becomes a negative 2x. All right, so we have what we want to maximize, but we want it to be in terms of only one variable. So we're going to look to the other information that we're not asked to maximize and see if we can find something there that relates the two variables together in such a way so that we can solve for one of the variables. Now, what do? Well, if y is equal to 3,000 minus 2x, we're going to take this and I'm going to substitute it in place of y in my maximization, so my optimization equation. So we want to maximize area. And we're going to say x times, we're going to replace the y with 3,000 minus 2x. All right, so I'm going to write this now as a function. So a of x, so it's a function of x, so it only has x's in there. And I'm going to distribute the x into the parentheses. So it's 3,000x minus 2x squared. So we want to say, well, what do we want to do? We want to optimize now the function over its domain. Well, what do we mean by domain? Well, we want to come up with a closed interval, a maximum and a minimum value that makes sense for x. All right, so what's the maximum and the minimum? Well, the minimum value that x can be is 0. Okay, because we can't have a negative amount of fencing. I can't have a negative width. What's the maximum? Okay, well, one thing we want to think about is we definitely want all of our variables to be greater than 0. That's a very logical boundary. They have to be greater than 0. So this would imply that x is definitely greater than 0. But we also want y to be greater than 0. So if I want y to be greater than 0, what I really want then is this expression, 3000 minus 2x. If I want this to be greater than 0, then I need the right side also to be greater than, let's say, or equal to 0. So what restrictions does that put on x? Okay, so we have our restrictions. Let's write that down. That's what's going to help us come up with this boundary. We know we want x greater than 0. We know we want y greater than 0, which y greater than 0 implies that 3000 minus 2x must be greater than, let's say, equal to 0. Okay, so let's solve for x here. So if I solve for x, I'm going to subtract the 3000, we'll bring it to the other side of our inequality symbol, and we'll divide both sides by -2. Now remember, when we divide by a negative, we have to flip our inequality symbol. So this means that x has to be less than or equal to 1500. So that's the maximum that x can be. It has to be less than this number. So our boundary, keeping all of those values positive, means that our boundary for x has to be 0 to 1500, and it can't be anything outside of those boundaries. Okay, so what we're talking about here is basically trying to get restrictions on x because our equation here is in terms of only x. All right, so we're asked to maximize the area. So we want to find the absolute max of the area, just like we did in section 4.4. So in order to find the maximum area, we need to take the derivative. So we're going to find the first derivative of our area. So that's 3000 minus 4x. All right, and we want to figure out what makes the first derivative equal 0. Okay, this is exactly like what we did from here on out in section 4.4. All right, so we're going to take our derivative, 3000 minus 4x, and I'm going to set that equal to 0. So I'm going to subtract over, once again, my 3000. And then I'm going to divide both sides by -4. So I get x is equal to positive 750. All right. Okay, well, if I wanted to make sure for sure that this is the absolute max, I could take my original function that was dealing with area, and I could plug in not only the critical number of 750, but I could also plug in my boundary points of 0 and 1500. All right, if you plug those into the original equation, 3000 times 750, so we're plugging into our area, 3000 times x, minus 2, and then 750 squared. If we do that, then we get a maximum area of 1,125,000 square yards. Okay, now if I test the boundary points, I end up getting 0 for both of them, and I'll leave the calculation to you there, but end up getting 0 for both of those boundary points. So this is definitely our maximum area, and it occurs when x is equal to 750. So let's go back up and figure out what that means. So if x is 750, I'm going to go back up to my picture here that we drew. If x is 750, then that means that the width of our rectangular fencing is 750 yards. Okay, and the length has to be what? Well, if y is equal to 3000 minus 2x, if I wanted to figure out what y is, I could always go and substitute 750 back in place of x. So that would be 3000 minus 2 times 750. That's 3000 minus 1500, which gives me that y is equal to 1500. Let's test this out. If I add 1500 plus 750 yards plus 750 yards, that equals 3000. So it all makes sense and adds up to give us the optimization solution that we want. All right, so our maximum area, 1,125,000 square yards if the width of our rectangular fencing is 750 yards and the length is 1500 yards. All right, for this example, it helps to have a nice visual of what's going on. One thing that I would encourage you to do is take a piece of paper, and this is what I do usually when I'm in class, is that we have this piece of paper. In the example it says cardboard, and what we want to do is we want to cut squares out from the corners of the piece of paper or the cardboard. So I would actually encourage you to do this, and since they're squares, then these lengths have to be exactly the same. So get a ruler out, measure like an inch squares at the corner of the piece of paper, cut out those squares. So they're not there anymore, so we'll just kind of visually cut those out. And then fold it up. Fold up the piece of paper to make a box. So this would look like here the bottom of that box right here. And then these flaps right here would fold up to be the sides. So this represents kind of the bottom of that box. So I encourage you to do that with a piece of paper so it gets a little bit better visual there. So the cardboard here that we're folding to form this box is originally 15 inches long and 8 inches wide. All right, now here comes the key here. If I actually fold it up and I cut out those squares and I fold it up, then what are going to be the dimensions of this box? So here's what we want to imagine. Something that looks a little bit like this. So I have my kind of the side of the box, and I have something that looks along these lines here. Okay, so and then let's imagine like this is kind of the bottom of the box here, and the box is an open box. Okay, well, if I fold up these flaps, then the height, okay, the height of our box would be x. Whatever x is, how much ever I cut out from the sides of the box, for those squares, the height will be x. Okay, what would be the width? And so we want, x 8 was the original width of that box, but we cut out and we folded. So how much did we lose? Well, we lost x here and x here. So the new width of our box turns out to be 8, but we took away 2 x's, so 8 minus 2x. All right, so the width here is 8, take away 2x. What about the length? Well, it was originally 15 inches, but then we cut out this x and we cut out this x as part of the sides and folded them up, so we lost that. So what is the new length of the bottom of our box? Well, it's 15 inches to begin with, but then we lose 2x. So the new length of the box is 15 minus 2x. All right. So we kind of described the box that we were presented with there. What are we asked to maximize? Well, we're asked to maximize the volume. All right. So let's find a good representation for the equation for volume. Okay, remember that volume is length times width times height. And of course, it doesn't matter the order that you put these things in, length times width times height, you can multiply in any order that you wish. Okay, now we want to be in terms of only one variable. Okay, now that we've actually described the box here in terms of x, after we folded that piece of cardboard, now we have the height, we have the width, and we have the length all in terms of x. So this is actually a really nice, easy substitution. So we'll write that as a function of x, and we'll just multiply them together in any order. So height is x, times the width, that's 8 minus 2x, times the length, that's 15 minus 2x. So all we have left now is we can multiply all that together if we wished. And then we need our restrictions. So let's look at what are the restrictions on our function. Well, one thing is the logical restrictions are that all of the dimensions of this box have to be larger than 0. So I need the height, the length, and the width to be larger than 0. So what does that imply? Well, that implies that x has to be greater than 0 because x and h are the same thing. That if w has to be greater than 0, then that implies that 8 minus 2x has to be greater than or equal to 0. Okay, we can put the little equals there if we want. And that also implies that if the length has to be greater than or equal to 0, then 15x 15 minus 2x, which represents the length, also has to be greater than or equal to 0. All right, so since we have a bunch of stuff going, I'm going to make a little number line for this. X has to be greater than 0. So I'm going to use red here just to kind of describe our descriptions here. So x has to be greater than 0. 8 minus 2x greater than 0. Let's solve that equation really quick. That would give me minus 2x greater than or equal to negative 8. So bring that 8 to the other side, divide by negative 2. I get x has to be less than or equal to 4. So we'll keep that in mind. When we divide by negative, we have to flip our inequality symbol. And so 4 would be over here. But this is saying that x has to be less than 4, which means I can use anything less than 4, but I can't use anything greater than 4. Okay, what about the length? What restriction does that put on us? All right, so let's solve. We'll bring the 15 over to the other side. I get negative 15. Divide both sides by negative 2. I end up with x has to be less than or equal to 7.5 or 7.5. All right, well 7.5 is over here. And it's saying less than or equal to, so that means I have to go in this direction. So what's our boundary? Our boundary turns out to be where you see all three of them overlapping. So our boundary is going to be where we see red, green, and blue. So the boundaries actually go between 0 and 4. So the boundary for x has to be between 0 and 4. So it can't be anything outside of those bounds. All right, so now that we have our bounds, we have our equation that we want to maximize in terms of only one variable. Now let's work with finding the derivative of this function, and then finding the critical numbers, and then testing all of our points. Okay, before we do the derivative, before we find that, let's multiply things together. I'm going to go ahead and multiply in the x. Okay. I'm just going to rewrite this function just to make it a little bit nicer to take the derivative of. So I'm going to multiply in the x, and then I'm going to FOIL these two binomials together. All right, so first times the first, I get 120x. Let's see, outer times the outer, I get minus 16x squared. Inner times the inner, I get minus 30x squared. And then last times the last, I get plus 4x cubed. Combine my like terms. And I'm going to rearrange to put from largest exponent to smallest. So I'm going to write this as 4x cubed minus 46x squared, combining these two, and then lastly a positive 120x. Now this is going to be a whole lot easier to take the derivative of because I can just use the power rule. I don't have to worry about the product rule or doing anything too crazy. So the first one, 4x cubed, I get 12x squared for the derivative, just using that power rule. 2 times 46, I get negative 92x. And then, of course, for the last term, I get 120. All right, remember we're going to set our derivative equal to 0, and then we're going to solve for x. So we're going to do a little bit of factoring here. All right. Greatest common factor, looks like it's going to be 4. They're all divisible by 4. Instead of factoring it out, let's just make this a little bit easier on ourselves. We're solving an equation, and so we can divide everything through by that common factor. So we end up with something much easier to work with. We end up with 3x squared minus 23x plus 30 equals 0. So an easier equation to solve. And we're going to factor this. Let's see, I get 3x and x. And for my signs, they both have to be negative. And I'm going to try, I'll have options of 1 and 30. Let's see, 2 and 15, 3 and 10, and 5 and 6. So I'm going to try 5 and 6 first. I'm going to put a 5 here and a 6 here. And I believe that is the factorization we want. We can FOIL it out just to check it, but I think we're good to go. So I'm going to set each one of those factors equal to 0. Oops. And then we're going to solve for x. So I get x equals 5/3 and x equals 6. All right, so remember what we want to do next is we want to plug this in to the original function, which is right up here. So I want to plug everything in, my boundary points, and also any critical numbers that I find within the boundaries. I'm going to plug them into the volume function that we have here. I'm going to give myself a little bit more room. Okay. So one thing we want to be careful about is what was our original boundaries. The original boundaries was from 0 to 4. So these are the only x values that I care about between 0 and 4. Which is kind of nice because one of these values that I get falls outside of the bounds. It's not in the interval that we were asked to look at. So we're not going to test that. So we're going to test 5/3. We can test 0, and we can test 4. So we can test the boundary points and also the 5/3 point given in the problem there. I get 4 5/3 cubed minus 46 5/3 squared plus 120 times 5/3. So we'll plug that in, and you can plug this directly into your calculator and give myself a little bit more room there, and see what the value of that volume would be. Alright, so when I plug all of that into my calculator, I end up getting 90.74 cubic inches. And nicely enough, when I plug in 0 and when we plug in 4, and I'm going to leave those calculations to you, plug those in place of x back into our original function, which we said was right up here. And what you're going to get really quickly for 0 is you'll get 0. And when you plug in 4, you also get 0. So this is definitely our maximum volume. And it occurs when x is equal to 5/3. So if x is equal to 5/3, then we have our maximum volume. So we have our maximum volume here. What would the length and the width and the height of the box be? So let's just check that out. Okay, so if x is 5/3, what are the other dimensions? So here's my 5/3. If x is 5/3, then my width, let's see here, the width is 8 minus 2 times 5/3. My width turns out to be 8 minus 10/3. Alright. And if I write that with a common denominator, let's see, that's 24/3 minus 10/3. I end up with 14/3, and written as a mixed number, that's 4 and 2/3 inches. So this turns out to be 4 and 2/3 inches long. So this is 5/3 inches. And what about the length? And so I'm going to just erase this and go for that length. So the length of the box would be 15 minus 2 times 5/3. So that's 15/1 times, or minus, let's see, 10/3. Again, give a common denominator. I end up with 45/3 minus 10/3. So that's 35/3 inches, which when I write that as a mixed number turns into 11 and 2/3 inches. All right. So the dimensions of our box, the height would be 5/3 inches, or 1 and 2/3, either way you want to think about that. The width would be 4 and 2/3 inches, and the length of the box would be 11 and 2/3 inches. All right. Our last problem here is working with minimizing packaging cost. So let's look at this problem here. It says, what are the dimensions of a closed rectangular box that has a square cross-section and a capacity of 128 cubic inches, and we want to construct it using the least amount of material? So a capacity of 128 cubic inches, that's actually describing the volume. So the volume is 128 cubic inches, or inches cubed. Okay, what do we know here? So this is, we're going to kind of write what we know. We know that volume is length times width times height. And we're actually given in the picture here, we're given that the width of the box is x, the length of the box is also x, and the height of the box is y. So we already kind of have an equation that we're working with here. We have length is, we said x, the width is x, and the height is y. So that's pretty nice. Let's just review one little thing. What do we ask to maximize or minimize? Let's see. It says use the least amount of material. So it sounds like we want to use something, we want to kind of go as small as possible with the amount of material. So the less material that we use, the cheaper it is to actually have the box. So basically I want to spend as least amount of money on the material as possible. So I'm going to use the smallest amount of material that I can, but I want the box to be able to hold as much as possible as well. Okay, so the capacity is over here. What do we actually want to do then? If I want to use the least amount of material, it sounds like I want to minimize something. And the material is on the outside edges of the box. So this sounds like surface area. So I would like to minimize the surface area of the box. The less material I use, the cheaper it will be, the less I pay in material cost for materials. All right, so that's what we're looking at. So we want to keep in mind something here, that this is my goal. My goal is to minimize the outside edges of the box, or minimize the surface area. Okay. All right. So we have everything we know about the volume over here. Then we have our goal is to minimize surface area here. So surface area, what I want to think about then is the area of each edge or side of the box. So what is the area of that surface? Well, the height is y, the width is x. X times y would represent the side of the box. That would be x times y. Well, how many sides do we have? Looks like we have 4 sides. So x, y. On the back side, we'd have xy, and then on this side, we'd have xy. So all of the sides is what we're describing. Looks like we have 4 sides, so we're going to write this as 4 times xy. So this represents all 4 sides, so all the areas of those sides. All right, well, what about the top of the box? So let's be careful there. What about the top of the box? What are the dimensions there? Well, it looks like a square box. We have x for that, and then on this side right here it says that this length is x. So this is x and this is x. So how do I find the area of that? Well, I add length times width, or multiply those dimensions together, I get x squared. So that's for the top of the box, and also we need one for the bottom of the box. So this is for the top and for the bottom of the box. So all those surface areas is what we want to add up together. So what does this look like? So we're going to minimize our surface area. That's 4xy plus 2x squared. All right, well, our goal is to minimize the surface area, but this equation that we have is in terms of x and y. So we want to be only in terms of x's if possible. Okay, so let's come back over here to the capacity that we were given. That we know the volume was 128 cubic inches, so we don't want that to change. That's a set fact of what we want to have in our box. So is there a way that we can rewrite this equation so that everything is in terms of y? Y by itself on one side and x on the other. One little part that I want to adjust here is that we know the volume is going to be equal to 128 cubic inches. So let's replace volume. Let me get rid of that square too. Let's replace volume with what we know, 128. That way we're kind of minimizing our variables here. All right, well, I want to get y by itself on one side because that's what I want to replace. I would love to replace this y with something that had x's in it. So let's divide both sides by x squared. Now if I do that, we get y equals 128 divided by x squared. So we're going to put that into our equation here in place of y. So now we're going to have a minimum. And we have 4. Let's write that as a function of x. Let's just call this s. Let's call this our s function. Okay. So when you write your equation, I want to see that you're minimizing. So give me the minimum. And then we'll just call this a function of s. We'll say surface area s of x equals, let's say 4x times y, which we know what y is now, plus 2x squared. So the y value now, we're going to replace y with 128 divided by x squared. So now we have our equation all in terms of that one variable. Let's simplify a little bit. this is like 4x divided by 1, 128 divided by x squared. So we end up getting something a little bit nicer. We end up getting, let's see, 4 times 128 over this x will cancel with this x, will leave us with 1x at the bottom. And then plus our 2x squared. Sorry about that. Try to get rid of this box. There we go. All right, so 4 times 128, let's multiply those together. We get 512, I believe, plus 2x squared. And we know we're going to take the derivative of this, so let's go ahead and write this with our exponents in the numerator. So I'm going to bring this up to the top, so it's going to be 512 times x to the minus 1 power plus 2x squared. All right, what are our restrictions on x? We wanted to know that as well. The only thing that we know is we want all of our variables to be greater than or equal to 0. So let's look at our restrictions. We want x to be greater than or equal to 0. We want y to be greater than or equal to 0. So this is a given. We're going to start at 0. For y being greater than 0, we want 128 over x squared to be greater than 0. If you think about it, this is already greater than or equal to 0. It doesn't matter what x value that you put in. If we square it, it's going to be positive, and then we have a positive divided by a positive, so this is always positive. So it doesn't matter what x value we put in after that. So our restrictions are not very strict here. It says it goes from 0 to infinity to make sure that x is greater than 0 and y is also greater than 0. So I'm going to put that next to my equation. 0 to infinity. All right, well, now that we have our function, we want to take the derivative of this. So we get negative 512 times x to the negative 2 power plus 4x. All right, so now we want to set this equal to 0. So before I do that, I would like to bring down now the variable back into the denominator to make it easier to work with. All right, I'm going to start to solve for x. So what I'm going to do is I'm going to bring over the 4x to the other side. Let's actually keep everything positive. I'm going to do it the other way. Let's bring the 512 to the other side. So we'll leave 4x on the left side. Sorry. And we'll write this as positive 512 divided by x squared on the right side. The reason I want to do that is because now I have a fraction equaling a fraction, and so I can cross multiply. So I get 512 equals 4x squared. Sorry, x cubed. Sorry about that. Now I can divide both sides by 4. So let's see what we get here. We get x cubed equals 128. And then I'm going to take the cube root of both sides. So I get x is equal to the cube root of 128. And that turns out to be approximately 5.04 inches, rounded to the nearest 2 decimal places. All right. All right, so our solution, 504 inches. Let's come back up to the top and see what the dimensions of our box then would be. If x is 504 inches, so we have 5.04 inches here for the width, 5.04 inches for the length. What about the height of the box? Okay, the height of the box, 128 divided by x squared. So to find the height, I'm going to take 128 divided by 5.05 inches squared, and you actually turn out to get something that's pretty close to 5.04 inches as well. So basically we need a cube. We need all of those dimensions to be exactly the same. What is our minimal surface area? So let's go back down and make sure we find that. Let's go back down to answering our question, which was, what is the minimum surface area then? Well, to figure out what that minimum surface area would be, let's take that solution we got for x, erase that there, and let's put in our 5.04 into our surface area function that we started out with. I'm going to plug it into this one that has the variable in the denominator already. So it's 512 divided by 5.04 plus 2 times 5.04 squared. Throw that in the calculator basically exactly as you see it there, and we end up getting a minimal surface area of 152.39 inches. And of course it's squared because we're talking about an area. Alright, so our minimum surface area, we find that by taking our x value, our critical number there, and plugging it back into the original equation. So we plug in our critical number. We only have one critical number. Remember our bounds was going from 0 to infinity. So if I plug in 0, I'm going to get 0. So, and actually, can I even plug in 0 into this equation? And I can't, because then I'll get something that's undefined. So really the only thing that I can plug in to test out for comparison of minimal value would be 5.04. So it's kind of nice. So this is the only thing that I can actually plug in. And so this is our minimal surface area, and then we can use that x value to determine the dimensions of the box.